Hi there, welcome back to Storytime with Miss Lindell and Ender, who's currently trying to chew on my hand. Stop that! Alright, so today's story is all about area. So this is the story of Hector and Vector and the roped off area. So we have Hector and Vector. Hector says that he wants to minimize the roped off area. It's okay. Vector says he wants to maximize it. So we're going to show they've got 20 feet of rope. We're going to try to maximize and minimize the area with them. So first we're going to start with Vector's way, maximizing. That's simpler, at least I think so. So they have 20 feet of rope, so that's how big the perimeter can be. And then we're going to look at some possible rectangles that Vector's thinking here. So first he starts off with a 9 foot by 1 foot rectangle, and he gets an area of 9 square feet. So he's like, well, that's great, but let's go down, try an 8 by 2. And it turns out you get 16 square feet. So he's like, great, that's bigger. Let's keep going. And he notices that as the numbers get closer together, the length and the width, the area increases. So he's got 7 and 3, gives you a 21 foot square. 6 and 4 gives you 24 square feet. And then lastly, he goes, oh man, this has got to be it. 5 times 5 is 25. That's probably the biggest rectangle I can make. So we'll look at the math behind it later, but that's Vector's conjecture. Go get it. All right. Then we've got Hector, on the other hand, who wants to minimize. So he also starts with a 9 by 1 rectangle and gets 9 square feet. But then he goes, what if, since bring the numbers closer together maximized the area, what if taking the numbers further apart for length and width maybe that would decrease the area? So he tries it. He goes 9.9 feet by 0.1 feet and gets an area of 0.99 square feet. So that goes in the direction that he wants it to. Then he tries, well, what if I went 9.99 feet by 0.01 feet? Well, then he gets a 0.0999 square foot rectangle. So he says, what if I keep going? What if I go 9.999 feet by 0.001 feet? Well, then he gets 0.009999 square feet. And so he's going, wahaha, I got this. And Vector's going, stop, soon there'll be nothing left. And he's kind of right. Just a minute, buddy. Because then he keeps going, 9.999 with 6 nines after it, and 0.000001 feet to get a 0.00000999999 square foot rectangle. So it's getting smaller and smaller and smaller as we keep getting a ridiculous amount of nines here, and then progressively smaller on the other lengths. Okay, so the math behind it. Let's look at how area and perimeter are related for rectangles. So perimeter, if you think about it as being, length and width, would be 2L plus 2W. So 2 of the length and 2 of the width added together. And in this case, we know it's going to equal 20. So, and we also know for area is length times width. Yeah, I know it's almost dinner time, buddy. So then, what if I put the length in terms of the width? So I subtract 2W from both sides, I divide by 2 on both sides, and we get that length is 10 minus W. That's how they're related in this situation. So I plug that in up here for length. We get 10 minus W times W, which if I distribute this, we get 10W minus W squared, a quadratic, which is really easy to maximize. Because if you look at or if it's a, in this case, it's negative right in front of the W squared, so it's a upside down parabola. So we get this kind of shape here. And to maximize it, well, that would just be wherever it's at the top, right? The vertex. So we got to look at the vertex on the graph. In this case, the vertex is at the coordinate 525. So that tells me that the width is 5 and the area is 25. So if I make the width 5 and the length 5, then the area will be 25, and that's the top of the parabola there. The vertex on the graph So that's our largest area. Minimizing it, on the other hand, is a little bit more difficult because if you retain that it must be a rectangle, so it has to have 4 sides, right? Then the minimum area approaches 0, but you can't ever make the length 10 and the width 0, or vice versa, because then it wouldn't be a rectangle, right? So the minimum, as you saw with Hector's idea, is that it goes towards 0, keeps getting closer and closer to 0, but it never actually reaches 0 if it must be a rectangle. Anyway, fun stuff, right? That's all with story time with Miss Lindell and Ender for today. Gotta go get Ender some dinner. See you guys later.